So I'd like to find, this pen feels weird. It was just my hand. For f of x equal to e to the negative x squared plus x. I want to find, there's a couple ways you could write this. I'm going to write it kind of a terrible way first. The derivative of f inverse evaluated at x equal to 1. Normally, often people prefer to write this as the derivative of f inverse with respect to x. Before we do this problem, I kind of want to back up a little bit because I always find this a bit confusing. So just as a reminder, here's kind of the idea. F of x looks like something. I don't know exactly what, although I do know that f of x is an increasing function. It always gets bigger from left to right. More generally, typically when someone asks you this kind of question, the function has to be invertible. Fun fact, functions that are always increasing or always decreasing are kind of the only functions that are actually invertible without doing some sort of restriction on their domain. If you want to pass the horizontal line test, you can't change direction, right? If you're going up and up and up and up and up and then start going down, oh, you don't pass the horizontal line test anymore. Or vice versa, if you go down and down, you can't start going. So functions that are always increasing and always decreasing are actually kind of the only functions that are ever wholly invertible. I'm going to make this one up. I don't know exactly what it looks like. It's like probably vaguely exponential, but I'm just going to say it looks like that. And I want to find the derivative of the, so let's say this is f of x. And this is, I want to try to draw this so it doesn't look supremely like what I'm thinking of. I've not drawn that super well. Sorry. Wow, yeah, I don't love my picture here. I'm gonna draw another one. This one's not good enough. Sorry. Sometimes you make a terrible picture mistake. So let's try that again. So I do want them to look like inverses. I just didn't want it to look exactly like e. You know what? Why not use the tools we have available to us? Let's do some Desmosing. Sorry, one sec. Sure. So let's actually see what this looks like. Oops, we've got f of x equal to e to the negative x squared. Not increasing, but then we're going to add on an x. Always increasing. Kind of cool. So also we can find the inverse. That's one thing I really like. I can't kind of emphasize enough how great it is that you can just totally switch x and y and get the inverse relationship. So if I graph x equal to e to the negative y squared plus y, check that out. Totally the inverse. Kind of awesome. And so here's the deal. We've been asked, as a reminder, to find the derivative of the inverse at x equals 1. So let me pull that back up. Sorry. So here's my inverse function in blue, and we're trying to find the slope of the tangent line right there. That's what we're trying to do. And I really hope it's. I'm gonna change this question just a little bit because I want it to be. I have a good reason for this. I'm gonna change it up. Yeah, let's make it like that. Whoops. Okay, I'm changing the question so everyone can see. There's a good reason for this, I promise. I'm not just doing it for the sake of doing it. We've got it to it. Here's what I want you all to observe. The slope of the tangent line here is the reciprocal of the slope of the tangent line there. I could draw them in there if you really need me to, but I'm just going to draw them on this piece of paper instead. So let's try and make this look relatively nice. Let me grab this over here. You guys watch me fail at trying to draw this picture decently. So we've got 1, 0, 0, 1, and this one kind of looks like this. This kind of this deal. Sure. And here's the mirror image of it in the other line. That's all right. You guys would accept that, I hope. Okay. And they're definitely reflective of each other in the line y equals x. And we're interested in finding the slope of the tangent line right about here-ish. And to answer that question, we're going to find the slope of the tangent line over here instead. And we're going to say that the slope that we actually want to find is equal to 1 over the slope that we're going to find. That's the whole gist of this inverse derivative theorem, is that instead of finding the derivative of the function that you're actually being asked to, you're going to find the derivative of the other function at the other point and take the reciprocal of that. Okay, let's do some labeling. I want to do this kind of generally. So I'm going to call this point here A comma B, even though I know it's 1 comma 0. And the point of interest on the other function is literally the point where the A and the B are interchanged, right? This point over here is B comma A. So I'm really interested in finding, I'm going to call it, right, this is the function, this is my F inverse of X. This is my F of X. And I want to find the derivative of F inverse with respect to X at X equal to what? On my picture here. Is X equal to A or is X equal to B? It's not a trick question. I'm looking at the green function. I'm at this point right here. What's the X coordinate? Right, totally. Well, yeah, you're right. It's 1 really, but I'm calling it A for the moment just to write the general formula. You're right. It's definitely 1. Okay. So, and then what we've said is that this is going to equal 1 over the derivative of the other function. So it's going to be 1 divided by the derivative of the original function, evaluated at what? Right. Or as people often write it, this is where things get super funky. I'm trying to remember what I wrote before. Yeah. We're going to evaluate this at X equal to, some people write B, some people write X equal to F inverse of A. Those are equally good. Someone might even write this as X equal to F of B. The whole point is that wherever you're evaluating this, it's the inverse value of this. Right. So if you're evaluating, if you're trying to evaluate the derivative at X equal to whatever, you should be having the inverse value over here. Okay, so back to the example at hand, which I know I've kind of, let me just write it again because I feel like I kind of jacked it up over there. So we were trying to do this. We were for F of X equal to e to the negative x squared plus 2x. We wanted to find the derivative of the inverse at x equal to 1. And so what we're actually going to find is the derivative of the inverse evaluated at x equal to 1 is going to be 1 over the derivative of the original function evaluated at where? It is going to be, someone said 0, right? I did just, I feel like there's someone in the other room, maybe it sounded so quiet. Right, it's going to be x equal to f inverse of 1, which happens. So the whole idea here is that usually they make it so it's something you can just guess, right? So f inverse of 1 is definitely going to be 0 because we can see that f of 0 equals e to the 0 plus 2 times 0, which is 1. which is the same as f inverse of 1 equals 0. So that's the idea here. I could have made this easier if I was a nicer person and said, I want you to evaluate the inverse function at x equal to f of 0. And then it becomes immediately obvious that, oh, if x is f of 0 here, then it's 0 that I should be plugging in over here. I think that's what the homework problem actually kind of does for you. So it's even nicer than I would be. And then we just do the thing. It's going to be 1 over the derivative of this function. If you have to use the chain rule, derivative e to the stuff is e to the stuff times the derivative of the stuff. And then I'm going to add 2. That's my derivative evaluated at x equal to 0. And plugging in 0, I get 1 times 0 plus 2. So I end up with 1 over 2. Looking back at the graph, this seems totally reasonable. Sorry, I don't want to cover that up for you guys, but if we look at the graph here, you can totally see, oh yeah, right there, the slope of the tangent line is definitely, sorry, I've covered things up. And we could actually write the slope of the tangent line if you really want to. It's definitely sure, there it is right there. There's this one tangent line, which is the slope of 1/2. And then the other one is for sure, right? Those slopes are reciprocals, y equals 2x plus 1. Is that all great? Yeah. So these inverse functions have reciprocal slopes at corresponding points. That's the best way I can say it. The formula is unwieldy, right? It's a weird kind of formula to use. And although you can use it to find derivatives of inverse functions, in general, I don't recommend it. So, questions before we move on to finally getting to the inverse trig derivatives. I know I've said that like the last 2 or 3 classes. Actually going to happen today. And then we can probably talk about like the mean value thing. Okay. All right, so oh yeah, you might want to thank you. Of course. Oh, that works too, sure. But I want this back over here. So okay, great. So inverse trig. Let's start with this, the functions actually. It's good to know about the inverse trig functions. I'm not going to graph all of them, but definitely we should be aware of a couple of them. So if you look at y equal to sine of x, it looks like this. Got a period of 2 pi. And kind of does this deal. It goes up to 1, down to -1. And sine looks like that. And from what I just said, talking about derivatives of inverse functions, is the sine function invertible as is? Definitely not, right? The sine function, if you just try to interchange x and y, you're not going to get an actual function, right? If you do x equal to sine of y, look what you get. Well, we're really just writing the sine graph now on the y-axis instead of the x-axis. So instead of the point 0, 0, I get 0, 0. Instead of pi over 2, 1, I get 1 comma pi over 2. Instead of pi over 0, I get 0 pi. And it kind of does this deal. And the same thing down this way. And that's not a function, right? It really, really, really fails the vertical line test a lot. So what do we do when we want something to be invertible but it isn't? We restrict it. We say, I'm going to take just a piece of this function where it's 1 to 1. So I'm going to take the sine function from negative pi over 2 to pi over 2. Is that the only region we could select? No, you could totally make a different choice. Does anyone ever make a different choice? No. We have collectively decided across the world that for sine, we're going to invert it, and the portion we're going to pick is the portion from negative pi over 2 to pi over 2. So the inverse part, which you can write as the inverse sine of x, or you can write as the arc sine of x, same deal. It's going to be just the portion where we're going to interchange x and y. So instead of starting at negative pi over 2 and then negative pi over 2, our y values are going to start at negative pi over 2 and then negative pi over 2. And our x values are going to start at negative 1 and then the positive 1. And it's going to look like this. It's just this section of the inverse relationship. So there's the entirety of the inverse sine graph. There's not a lot to it. Domain, negative 1 to 1. Range, negative pi over 2 to pi over 2. And it. And then I should point out, it's a good idea to know how to deal with the inverse sine function. So hopefully you guys remember how to evaluate trig functions. I know it might have been a little bit of a while since you have, but for example, we can find that sine of pi over 3 is the square root of 3 over 2. Or sine of pi over 4 is the square root of 2 over 2. And sine of pi over 6 is 1/2. The reason I write these things down is because then we can say, okay, well, the inverse function, like with every inverse function, just interchanges the roles of the input and the output. So sine of pi over 3 is root 3 over 2. The inverse sine of root 3 over 2 is equal to pi over 3. Or as I usually say, when I look at the inverse sine function or the arc sine function, is the inverse sine of root 3 over 2 is the angle whose sine is equal to root 3 over 2. Oh, that angle is pi over 3. But honestly, when I see inverse trig function, the first thing I think is the answer is an angle. I'm looking for the angle. What angle? The angle that if you took sine of that angle, you would get the number that's in the inverse sine function. And so in a similar way, the inverse sine of pi over 6, sorry, that's not what you usually do. I mean, there probably is an answer to that, but it's terrible. The inverse sine of 1/2 is equal to pi over 6. Because the angle that you take sine of to get 1/2 is pi over 6. I kind of like to liken it to exponential functions and logarithmic functions. We know that 2 to the 3rd is equal to 8. I'm thinking of my function as y equal to 2 to the x. So here the input is 3 and the output is 8. And the logarithmic function, y equal to log base 2 of x, inverts that. Now my input is 8 and my output is 3. I input the x value and I got out the y value. I input the x value and I got out the y value. That's all inverse functions do. They interchange the role of x and y. That's why you interchange x and y when you're trying to find the inverse function. I also want to point out that for sine, the negative values are really, really easy to deal with. Inverse sine of negative 1/2 is negative pi over 6. The angle whose sine is equal to negative 1/2 is negative pi over 6 down in quadrant 4. I should really, really emphasize the angle is not 11 pi over 6, right? You're not going counterclockwise all the way around to the 4th quadrant. You're going starting from 0 clockwise back negatively to the 4th quadrant. So whenever you're taking an inverse sine of something, your angle should always be between negative pi over 2 and positive pi over 2. It shouldn't be bigger than pi over 2, which 11 pi over 6 definitely would be. What else do I want to say about this? Not a whole lot. Yeah, let's talk about the other two that so there are 6 inverse trig functions we could talk about. We'll talk about the 3 main ones. We might talk about the other 3 less main ones, but they're kind of terrible in some ways. My wife is texting me things that I thought might be important, but are not. Okay, so inverse cosine, similar to inverse sine, but a little bit different. Let's graph cosine. And so cosine starts at 0, 1, and then goes pi over 2. So there's what cosine looks like. And just like the other function, right, it doesn't get to be invertible without making a restriction. Let me just close that door. Now, here's the disappointing part. The disappointing part is that we can't use the same domain to restrict this to, right? If we were to pick the same domain that we use for sine from negative pi over 2 to pi over 2, it wouldn't be invertible because it doesn't pass the horizontal line test. So instead, we have to make another selection. And the selection we make for this function is we're going to restrict it to the interval from 0 to pi. From 0 to pi gets you the entire range of the cosine function. I know there's not a lot of it, but you do get everything from -1 to 1. And you don't get any repeat values, right? From 0 to pi, cosine equals every value from -1 to 1 and nothing twice. Or in shorter words, it passes the horizontal line test. So here's the inverse function. I'm going to take that section there and I'm going to reflect it across the line y equals x. Or what I'm really going to do when I do my inverse function, I'm just interchanging every x, y coordinates. That's the easiest way I find to graph it. So instead of graphing the point 0, 1, I'm going to graph the point 1, 0. Instead of graphing the point pi over 2 comma 0, I'm graphing the point 0 comma pi over 2. Instead of graphing the point pi comma -1, I'm graphing the point -1 pi. It's going to look like this. Something that we're going to show shortly here, but I'm just going to point out, is that both arc cosine and arc sine, or inverse cosine and inverse sine, both of them are not differentiable at the ends. So the derivative of inverse cosine does not exist at x equal to 1. The derivative of inverse cosine does not exist at x equal to positive 1 either. I think it's the main one first. And what you can kind of see, hopefully if I've drawn it well enough, is that at those points, you would have a vertical tangent line. And the vertical tangent line doesn't have a slope that exists, right? It's not defined there. So both of these functions have derivatives that do not exist at the ends. What else to say about this? We could do, oh yeah, inverse cosine is a little fun here. So here's something that's kind of weird about inverse cosine. Yeah, not weird. So we could also evaluate, say, like the inverse cosine of the square root of 3 over 2. And that's going to be the angle that if I took cosine of it, I would get square root of 3 over 2, which is pi over 6. Or inverse cosine of 1/2 would be pi over 3. For inverse sine, the negatives are nice. You just go, you take the corresponding negative value. So if I know inverse sine of some number is equal to some angle, I know inverse sine of the negative number is equal to the same negative angle, right? Which we saw previously. It's not true for cosine, unfortunately. If inverse cosine of root 3 over 2 equals pi over 6, inverse cosine of negative root 3 over 2 is equal to, it's not negative pi over 6, right? Because I'll just point out the domain for inverse cosine is -1 to 1. but the range for inverse cosine is 0 to pi. So we're looking for an angle whose cosine is equal to negative root 3 over 2. It can't be an angle in quadrant 1 because everything in quadrant 1 gives you positive results. It's got to be an angle in quadrant 2. It's the angle with the same reference angle as pi over 6. It's 5 pi over 6. Because cosine of 5 pi over 6 equals negative root 3 over 2. In a similar fashion, inverse cosine of, sorry, I forgot a very important thing there. I forgot the -1. Apologies. That might, I saw the question you faced. I feel like that might be the issue. Inverse cosine of negative root 3 over 2 is equal to 5 pi over 6. And in a similar way, inverse cosine of -1/2 is equal to 2 pi over 3. And if you really wanted, inverse cosine of negative root 2 over 2 is going to be 3 pi over 4. Because cosine of 3 pi over 4 is equal to negative root 2 over 2. And the knowledge I was using there that I didn't actually mention was also inverse cosine of positive root 2 over 2 is pi over 4. Because cosine of pi over 4 is root 2 over 2. So really, I'm kind of using these values to then find the corresponding angle with the same reference angle in quadrant 2. So inverse sine is a little easier to deal with than inverse cosine when you're evaluating things. Okay. Yeah, let's go ahead and talk about inverse tangent, and then we will move on to finding the derivative of things. One more. So tangent. Tangent looks like this. Got vertical asymptote to pi over 2 and negative pi over 2. Those aren't the only ones, right? It's actually got an infinite number of vertical asymptotes. They're all spaced pi apart from each other. So there's another one over here, like 3 pi over 2. And tangent looks like this. And it has intercepts every pi. And the other points I like to keep in mind for inverse tangent are we have the point pi over 4, comma 1. So I know I've not done a great job of like graphing the scale, but that's okay. Right, tangent of pi over 4 is 1. Tangent of negative pi over 4 is equal to -1. So, as you might have noticed, just like the other two examples, this tangent function does not pass the horizontal line test. If you try to invert it, it looks super crazy when you try to invert it. In fact, in case you guys want to see it, here it is. If you want to take, so here's y equals tangent. Lots of all those. And let me turn that off for a second. Here's the reverse or the inverse function. Wow, it's a lot of not being a function. All right, that's definitely, we don't want that. So what we need is, instead of all of that, just this. Just that one there, which we get by taking all of this and restricting it to negative pi over 2 to pi over 2. And I clearly did something wrong there. Sorry. What's your problem? Okay, fine. You always have to press the arrows here, right? Okay, so there's the restriction that we actually want. We only want the part from negative pi over 2 to pi over 2, and then that when we invert that, we get the inverse function, inverse tangent of x. So we're literally just taking this section here and saying, okay, I'm going to find the inverse relationship, y equals arc tangent of x, or y equal to the inverse tangent of x. And maybe I've said this before, but I'm going to say it again for sure. Whenever you're thinking about inverse functions, you should think about all the x and y things changing. So I'm looking at just this part here. I'm going to get the same 0.00. Instead of pi over 4 comma 1, I'm going to get 1 comma pi over 4. And yeah, that's fine. 1's bigger than pi over 4. I'm going to get negative 1, negative pi over 4. And then this thing I said also holds for asymptotes. Meaning, in this graph, I have vertical asymptotes, x equal to something, but all my x's and y's interchange. So when I find the inverse function, all my x things become y things, and my vertical asymptotes become horizontal asymptotes. So instead of getting x equal to pi over 2, I get a horizontal asymptote of y equal to pi over 2. And instead of negative pi over 2 for a vertical asymptote, I get negative pi over 2 for a horizontal asymptote. And it looks like this. And here's a question that will probably come up, probably more likely next quarter. Something to be aware of. The limit as x goes to infinity of the arc tangent of x is equal to pi over 2. And also the limit as x goes to negative infinity of the inverse tangent of x is equal to negative pi over 2. These are limits you kind of just have to know graphically. There isn't really any other good way to know them. At least not that I can think of. So definitely kind of neat. And then you could ask the same sorts of things, like what's the inverse tangent of the square root of 3? Well, it's the angle whose tangent is equal to root 3, which is pi over 3. Or you could ask, what's the inverse tangent of negative 1? Well, I know the inverse tangent of 1 is pi over 4, because tangent of pi over 4 is 1. So the inverse tangent of negative 1 is negative pi over 4. Just like inverse sine, inverse tangent has negative answers when you input negative values. In fact, I usually think of inverse tangent and inverse sine having essentially the same range. It's slightly different, right? For inverse tangent, the range doesn't include the end values, but they're virtually the same. The domain for inverse tangent is everything. So there's the main 3 inverse trig functions you should be aware of. Yes, inverse cotangent is very similar to inverse tangent. Let me ask you all, have any of your teachers talked about inverse secant or inverse cosecant? Okay, then I will mention it, but I'm going to mention it briefly. So inverse secant is, well, both of them are funky. They both have problems. So let's look at y equal to secant for a second. And don't worry, after this, we will actually finally get to, okay, someone else said yes to. We're finally going to get to the derivatives of the inverse trig functions, but let's look at inverse secant for just a moment. So here's secant. And honestly, the way I've always graphed secant or cosecant is by graphing its reciprocal and then flipping it over. I'll show you what I mean. So secant is the reciprocal of what? Right. So I'm going to graph cosine. I'm not really going to graph cosine. I'm going to think about the graph of cosine. So I know that cosine has a period of 2 pi. And cosine starts at 1. And then hits 0, and then negative 1, and then 0, and then 1. And that's actually all I want from cosine. So here's the deal. Cosine, if I was going to graph it, gets smaller and smaller and smaller and smaller as we get closer and closer to pi over 2. So secant, well, secant's the reciprocal. If cosine gets small, what happens to secant? It gets big. So as cosine goes down to 0, secant is going to get infinitely large. And if cosine is equal to 1, 1 over 1 is going to be 1. And then over here, if cosine is equal to -1, secant is also -1 because 1 over -1 is 1. And then as the cosine function would get closer to 0, the secant function moves further away from 0. Same deal over here. As the cosine function would get closer to 0, the secant function moves further away from 0. So I kind of think about the secant function and the cosecant function as taking the original cosine and sine and kind of flipping them away from the x-axis. So right, there would be like this little hump here, and I've kind of flipped it away. There would be like this little hump here, and I'm going to flip it away. And the same deal over here to the left. So essentially, when I'm thinking about graphing secant, I'm saying, oh, well, I know that wherever cosine would be 0, I'm going to get vertical asymptotes. And wherever cosine would equal 1 or -1, secant would also have the same value. Okay, so here's the part that kind of sucks. There isn't agreement in the mathematical world on which section we should pick to take the inverse of. Some people, and I kind of go back and forth. There are good choices for making both. So some people like to pick this section. So one choice is to restrict secant to this section. The section that starts at the point 0, 1 and ends at pi. I'm sorry, fine, I'll just draw it this way. Sorry, I've kind of made this not like super excellent here. So here we're restricting the domain to people. I usually just write it from 0 to pi, but technically you should exclude the asymptote at x equals pi over 2. So people, it's 0 to pi over 2. Parentheses, because we don't want that value, union pi over 2 to pi. To me, this feels like the natural choice because it's the same, essentially the same domain that we picked for cosine. And you can do the same thing for sine and cosecant. The issue with this, well, when you find the issue isn't so much even the reciprocal, or sorry, the inverse, apologies. So I want to graph y equal to the inverse secant. Well, I'm literally just interchanging x and y. So this is 0, 1, I get 1, 0. I have a horizontal asymptote y equals pi over 2. And instead of pi -1, I have the point -1 pi. And then it does this kind of deal. And for me, I like this choice best. I think, some of the time. Here's the reason why I don't like this choice. And we're going to see this later on. I'll just tell you right now, if you take the derivative inverse secant here, and we'll show it in a little bit, but here, for this definition, for this inverse secant that I've just graphed, the derivative of the inverse secant is going to be 1 over the absolute value of x times the square root of x squared minus 1. Don't worry, we're going to come back and actually show why that is. But I just want to point out that we don't love this. We really, really, really don't like having to have an absolute value if we can help it. And we can help it. So here's what I'm going to show you. Some other people, also smart people, have decided they would prefer to make a different choice. They're going to choose, instead of this domain for the inverse, for the secant function, they're going to take, and I have to always remind myself, like, which part are they going to choose here? So here's the way I would usually think about making the choice for the domain. I'm always going to pick the first quadrant from 0 to pi over 2. It's always a good choice, right? I definitely have from 0 to pi over 2 for every one of the trig functions I've done so far. And then usually the choice we make is the adjacent quadrant that also gets you the rest of the y values. For cosine, that's quadrant 2 from pi over 2 to pi. for sine and tangent, that's quadrant 4, from 0 to negative pi over 2. Here, we can't choose quadrant 4 because it's not giving me the rest of the y values. We're deciding not to choose quadrant 2 because we're just making a different choice. We're going to choose quadrant 3 from pi to 3 pi over 2. So here's the region or the section of the secant function I'm actually going to graph, which I know seems super kind of sketch. There's my asymptote of pi over 2, and then here's pi, and then here's 3 pi over 2 where I have another asymptote. Instead of picking the point, instead of picking this section here, we're going to start here and pick this section over here. Oh, sorry, you might want to see the thing I'm actually trying to graph. Yeah. Good call. Which seems just bizarre, especially when you draw the inverse. Here's the domain we're restricting to. The domain is 0 to pi over 2 union pi to 3 pi over 2. Yeah. And then when we draw the inverse, so then the right side's still the same as it was before, right? We're still going to get this piece here. But instead of getting this piece here, we're going to get it going up like that over there. So we still have this asymptote of pi over 2. Oops, maybe don't kill your paper games. Also 3 pi over 2. And it looks like this. So this part here becomes this part here. And this part here becomes this part here. It looks really, really wrong. I definitely like the other graph better. Here's the other one. I like this one better because it just looks a little more symmetric, really. Like it just seems more nicely shaped. But here's the advantage to this definition. So this definition, the derivative of the inverse secant of x is equal to 1 over x times the square root of x squared minus 1. No absolute value needed. So your professor will probably, if they address this at all, will probably they probably won't talk about this at such depth that we have, but they might just say the derivative of inverse secant is either with an absolute value or without. They'll probably just make a choice. They might not even explain it. They might, I don't know. But then they'll expect you to kind of use whatever choice they make. So just be aware, your derivative inverse secant and also inverse cosecant might have an absolute value or it might not. And it wholly depends on how someone decided we're going to write the inverse secant function in the first place. And literally, there is no definitive answer. Some people choose it to be this inverse secant. Other people choose it to be this other inverse secant. Both are totally valid choices. And you're just going to have to, well, you're going to have to do whatever your professor says, right? I mean, I've decided this is what we're using. That's it. And I would say probably most people will probably make this choice because the derivative is nicer. No one wants to deal with an absolute value unless they have to. Okay, I think we finally talked enough about these things. We can actually talk about the inverse derivatives now. All right. Let's start with, well, in fact, we already did one of them, I know, a while ago. Let's go back and revisit it. So let's find the derivative of the inverse sine of x. There's a good way of doing this and there's an awful way of doing this. The awful way, I will just point out, you totally could use the inverse derivative theorem that we talked about at the beginning of class today. You can say, okay, well, I know, right? We know from before the derivative of f of x evaluated at This is where I always start to kind of blow it, to be honest. Evaluated it x equal to f of y, I feel like is what I want to write. That's, oh, except I want inverse, sorry. Yeah, the derivative f inverse at is the same as the derivative of, sorry, 1 over the derivative of the function evaluated at just, this is where this theorem is confusing, right? It's not like I think I really wanted this to be something else. I think I just want this to be y. I feel like I picked like the wrong letters here. Basically, whatever you're throwing in here, it should be the inverse of that over here. Okay. I don't really want you to use this theorem, but you totally could. So let me just point out, if I'm trying to find the derivative of inverse sine, you probably don't need to know this, but it's kind of cool. Well, so my inverse function is sine of x. My original function is cosine of x. Oh my God. Or maybe not. Maybe that's the derivative of my original function. What's my actual original function? That's not a dumb answer that I just said. It's really obvious. I just made it a mistake saying words. Maybe I also made a mistake there. Yeah, how about that? How about you get it right? Sorry, I'm making a few errors that are unforgivable. So if my inverse function is inverse sine, what's the original function? It's like, I don't know what he's talking about anymore. It's just sine. All right. Sorry, I made it like way more complicated than it needed to be there. Apologies. So what's the derivative of sine? Well, cosine. Okay, but now here's the thing that's a little bit wonky. I'm trying to find the derivative of inverse sine at x, and it's going to be cosine of the inverse of x, right? Which I know is kind of weird. This is where I feel like this is where it kind of starts to fall apart. So I'm going to write it this way. I'm going to say that, yeah, this is going to be 1 over cosine of y, where y is equal to my inverse sine of x. But I'd really like this to be in terms of x. So I'm going to solve for x here. X is, sorry, sine of y is equal to x. Okay, I know sine of y is equal to x. I'd really like to find cosine of y. So what do? There's two choices. You either use a trig identity or you draw the triangle. Sine of y is equal to x. The third side is the square root of 1 minus x squared using the Pythagorean theorem. And cosine of y is the square root of 1 minus x squared. And what I really, really, really want to say is you should never, ever do it this way. I know I've done it this way to show you guys that you shouldn't do it this way. This is a way some people might show you how to do this. I really hope they don't. But I just want to say you can actually find the derivative of an inverse function as a function by using this inverse derivative theorem. This is not the easiest way to do it. So let me now show you the better, easier, nicer way that you should all do all of these derivatives. Really, you should just memorize them at the end of the day. But here's how you actually want to do this. Write that. And if it helps, you can remind yourself that when you're taking the inverse sine, the outputs have to be between negative pi over 2 and pi over 2. This is minorly important. If you forget about it, it's not that big a deal. I want to find the derivative of inverse sine of x, but I'm pretending like I don't know how. So I'm going to do the thing we usually do when we're trying to find the derivative of the inverse function. I'm going to make it not an inverse. I'm going to rewrite it. I'm going to take sine of both sides. Sine of y equals sine of inverse sine of x is just x. This is also the way you might have found the derivative of the natural log of y, or of x, sorry, right? If you're trying to find the derivative of the natural log of x, you might have written it as y equals natural log of x, and then written e to the y equals e to the natural log of x, or e to the y equals x, and then taking the derivative of that using implicit differentiation. So the whole idea, when you try and find the derivative of an inverse function, is to undo the inverse relationship, right? Write it as the original relationship, but now you've got x and y kind of in the opposite spots that you usually have them. What's the derivative sine of y? What am I forgetting? Exactly. Derivative sine of some stuff is cosine of the stuff times the derivative of the stuff, and the derivative of x is just 1. Just like over here, if you took the derivative of e to the y equal to x, you would get e to the stuff times the derivative of the stuff equal to 1. And then you would get y prime equal to 1 over e to the y, but that's just 1 over x, which we know is the derivative of the natural log of x. So then I'm going to solve for y prime. Notice how I'm getting the same thing I got over here, just in a way that feels a lot more natural. At least I hope it feels more natural. I hope this feels less terrible than what I did over here. And then how are we going to find cosine y? Well, you could use a triangle like we did over here. I prefer the triangle method. So I'm going to say, okay, I know that my angle is y. I know that sine of y is equal to x. I know I'm doing the same work I already did, but I think it's worth seeing a couple times. So opposite over hypotenuse. And then you can find this third side by using the Pythagorean theorem, right? If I call this question mark for a second, and the question mark squared plus x squared equals 1 squared. So question mark squared equals 1 minus x squared. So question mark is the, actually, so I kind of obfuscated a little bit there. It's really plus or minus the square root. No, that's a, Okay, here's where it's really, really important to remember. Cosine of y is going to be this side over that. So it's going to be question mark, which is this. But let me ask you guys, my angle y, what quadrants is y restricted to? And what quadrants is cosine positive in? Aha! So the thing is, the angle always ends up in the right spot for the thing you want to have, the sign you want it to have. So even though it's literally true that this side is plus or minus the square root of 1 minus x squared, since our angle is in quadrant 1 or 4, it has to be the plus part, which is beautiful. So our answer ends up being 1 over the square root of 1 minus x squared. Ta-da! Now we'll talk about the rest of them. I will point out, and I'll say it at the end actually, because there is a nice connection here to make looking ahead towards 21B when you're trying to use trig substitution to integrate things. I know those are words you probably don't know what I'm saying. You will eventually, and be like, oh, James said this thing, and there's a nice connection between the inverse trig functions and their derivatives and trig substitution. I know, right? It's a ways off, but it's good to look ahead. So let's talk about finding the derivative of inverse cosine of x. And we're going to do it exactly the same way. We're going to say, all right, well, I'm going to write y equal to the inverse cosine. I'm going to then rewrite this as cosine of y equal to just x. Also worth noting here that our angle is in quadrant 1 or 2, right? Inverse cosine, the angles are between 0 and pi. And then we're going to differentiate both sides. The derivative of cosine of some stuff is negative sine of your stuff times the derivative of your stuff. The derivative of x, as it usually is 1. And then we're going to solve for y prime. You get y prime equal to negative 1 over sine of y. You totally could write cosecant there. You shouldn't. It's not really helpful. Because now we're going to do the same thing we did before. I'm going to use a triangle. I should mention you totally could use a trig here. You totally could say, okay, sine squared y plus cosine squared y equals 1, and then solve for sine. Sine squared of y equals 1 minus cosine squared of y. Sine of y equals plus or minus the square root of 1 minus cosine squared of y, but cosine of y is x. So cosine squared of y is x squared. And then just like the previous problem, the angle y is in the right place for this function to always be positive. Y is in quadrant 1 or 2, and sine is positive in quadrant 1 or 2. So you totally could do it that way. Or you could do it the triangle way, which honestly is the same work, just viewed differently. You say my angle is y. I know that cosine of y equals x over 1. Cosine is the adjacent of the hypotenuse. The remaining side is the square root of 1 minus x squared. And then sine of y is opposite of our hypotenuse, so it's the square root of 1 minus x squared. So here's a nice thing to observe. The derivative of inverse sine of x is 1 over the square root of 1 minus x squared. And the derivative of inverse cosine of x is negative 1 over the square root of 1 minus x squared. Not a coincidence. We're going to see that pattern repeat itself both for cotangent and tangent, and sorry, I should say inverse tangent and inverse cotangent, and inverse secant and inverse cosecant. It's always going to happen. Where if you know the derivative of the non-co-inverse trig function, then the derivative of the inverse co-function is literally just the negative of the other one, which is nice. It means you'll have to remember 3 things instead of 6 things. So let's look at the next one. Let's look at tangent. I should say inverse tangent. So we're going to find the derivative of inverse tangent of x. And we're going to do this literally. So at this point, I feel like you guys could probably do this just fine, right? It's literally the same steps every time. You write y equal to your inverse trig function. You rewrite it as the trig function of y equal to x. Differentiate both sides. Derivative tangent to some stuff is secant squared of the stuff times the derivative of the stuff equal to 1, not x, and differentiate both sides. And then you solve for y prime by dividing. Y prime is 1 over secant squared of y. Then you go and you fill in what secant squared is by drawing a triangle. And for our triangle, we're always using where tangent of y is equal to x, or trig function of y is equal to x. So my angle is what? Is it y or x? No, is it y or x? Do we take tangent of angles or inverse tangent of angles? It is a good question, brilliant. So how do I address this without just giving you the answer? I don't know how. I'm trying to think like this. We take trig functions of angles. Right? Sine, cosine, tangent. When you're evaluating sine, cosine, tangent, etc., you're always evaluating them at an angle, right? A tangent of 30 degrees. Usually we use radians. So cosine of pi over 6 radians. Sine of pi over 2 radian. So the angle is y. X is just a value. But we know that tangent of y equals x over 1, and tangent is opposite over adjacent. And then we can find the third side, again, using the Pythagorean theorem, This third side is going to be the square root of 1 plus x squared. I can show the work, right? I'm going to call this third side c. I know that 1 squared plus x squared equals c squared. So literally just square root both sides. C is the square root of 1 plus x squared. And I should mention my angle is in quadrant 1 or 4 because tangent, right? Inverse tangent has output to be in quadrant 1 or 4. And I'm going to be taking secant of that. And secant is the reciprocal of cosine, and cosine is positive in quadrants 1 and 4. So it all works out every time. Super nice. So here we end up getting that our derivative is 1 over secant squared. Cosine is 1 over that, so secant is that over 1. So secant of y is the square root of 1 plus x squared. It doesn't even matter if it's positive or negative because it's going to square it anyway. Secant squared is 1 plus x squared. So the derivative of the inverse tangent is 1 over 1 plus x squared. And I feel like, although we could do the work for inverse cotangent, I think I can just tell you the derivative of the inverse cotangent of x is negative 1 over 1 plus x squared. I would encourage you all, if you have the time, to do the work for it. You can start, literally the process is the same. You should do this you all should do this when you have a chance. Find the derivative of the inverse cotangent of x by writing y equals inverse cotangent of x, and then cotangent of y equal to x, and then so on. Take the derivative of both sides, et cetera, et cetera, et cetera. Worth doing, and you'll definitely get negative 1 over 1 plus x squared. Some people, oh, it's got water on my mask. That's great. Some people prefer to write this as 1 over x squared plus 1. It does not matter which way you write it, they're the same. But I don't know why. Sometimes people. Excellent question. How do I know the opposite side is x and the adjacent side is 1? So because of this right here, right? I started with y equal to inverse tangent of x, and then I rewrote it as tangent of y equal to x, or tangent of y equal to tangent of inverse tangent, right? Because tangent of inverse tangent of x is x. So the inverse function does. So then I made it convenient for myself. I know that, so Katoa, tangent is opposite over adjacent. And I want to make it work. Well, I know that tangent of y is equal to x. So I'm just going to say, well, x is really just x over 1. We could have done something different, right? You could have done something funky, like said it's 2x over 2, or 3x over 3, or whatever, 10x over whatever. But I'm trying to make the work kind of as easy as possible. So I'm going to make it x over 1, so I can call that x and that 1. But you're right, it's kind of like, yeah, we're just going to change our thing into the thing divided by 1, so I can find sides of the triangle to put on my triangle. Good question. Other questions about what we've done here? All right. Let's talk about inverse secant, and then we'll do some other stuff. I'm running out of paper. Let me go look and see if I have more paper. Oh, I got tons of paper. Yeah. So much paper. Paper kind of, I don't want to. Okay. So let's find the derivative of inverse secant of x. And we'll hold off on talking about what we're going to get until the very end. So same deal. Y equals inverse secant of x. We're going to rewrite it as secant of the angle y equals just x, which is really secant of the inverse secant of x, if you prefer. You don't have to think about it that way. You can just sort of think about, oh, if y equals secant of x, then y is the angle that if you take secant of it, you get x. Oh, well, that's exactly the statement I'm writing there. The words can be helpful. And then we're going to differentiate both sides. Okay, secant's always the weird one. Right, the derivative of secant of some stuff is secant of the stuff times tangent of the stuff times the derivative of the stuff. and the derivative of x is just 1. So now we're going to solve for y. Sorry, we're going to solve for y prime. Y prime is 1 over secant of y times tangent of y. One of these things is easy to deal with. Looking at what I've written on the page, what's secant of y equal to? It's definitely on the page somewhere. Secant of y equals something. Oh yeah, it's totally x. But to get tangent of y, we do need the triangle. So watch me here. I'm going to do the same kind of thing I did before. I'm going to use the fact that secant of y is equal to x, but I'm going to write it as secant of y equals x over 1. And then I don't ever remember what side secant is. I just know that cosine is adjacent over hypotenuse and secant is the reciprocal of that. Sorry, I said, yeah, adjacent over hypotenuse. So secant should be hypotenuse over adjacent. I'm going to draw my triangle like I always do. The angle is y. The hypotenuse is x. The adjacent is 1. And this third side is 1 squared plus question mark squared equals x squared. Question mark squared equals x squared minus 1. So my question mark is the square root of x squared minus 1. So that's what's going to go in for tangent, because tangent is opposite over adjacent. So tangent of y is totally going to be the question mark over 1, which is the square root of x squared minus 1. All right, so depending on how you define this, how you define inverse secant, you may or may not need an absolute value. Let me show you what I mean. So first I want to just point out, if x is positive, if x is larger than 1, so let me actually write something. So if I write the derivative of inverse secant of x equal to 1 over x times the square root of x squared minus 1. I just want to point out that if x is bigger than 1, is my derivative positive or negative? Well, if I pick a number larger than 1 and plug it in, do I get a positive or a negative number out? Positive, great. On the other hand, if x is less than negative 1, the derivative is going to be positive or negative. Definitely negative, because x is negative and square root always gives you a positive thing out. Okay, well, this totally sits well with one of the graph choices and does not sit well with the other graph choice. Let me remind you of our secant choices. Or sorry, our inverse secant choices. So here's the nice one that I like. Oh, they're both nice. I shouldn't disparage one of them. So there's one of them. And here's the other one that I don't like as much. So let me ask you all, which of these graphs does this derivative go with? The one on the left or the one on the right? It's definitely the one on the right. The one on the right is the one that has a negative derivative over here, right? If you think about the slope, or really it's decreasing, right? The function is getting smaller, the derivative is negative. You can also think about the slope of the tangent line, right? Any tangent line would have a negative slope over here. So this one is where the derivative of inverse secant is equal to 1 over x times the square root of x squared minus 1. This one, the sign on the left side is wrong, right? We need the derivative to be positive, not negative. So this one is where the derivative of inverse secant of x is equal to 1 over the absolute value of x times the square root of x squared minus 1. Kind of funky. So you just have to memorize which one your teacher has said and then go with that. All right. those are the inverse trig derivatives. I do encourage memorizing them. Actually, I suppose I should mention the last one, right? I haven't said that one. So you can totally do the same sort of process for inverse cosecant. I don't think we need to go through it. It is maybe worthwhile to do on your own. Let's just write them all out. If I can maybe ever change these here. And then I'm going to make a couple observations for you all that hopefully you'll remember when you get to trig substitution in 21B. So here are our 6 inverse trig derivatives. Here are the 3 you actually need to know. And then I'm going to write it without the absolute value. So we want to know the derivative inverse sine is 1 over the square root of 1 minus x squared. The derivative inverse tangent is 1 over 1 plus x squared. And the derivative inverse secant is 1 over x to the square root of x or minus 1. A couple of things I have noticed over the years about how I remember these. Tangent looks like a t, or I should say tangent starts with a t that looks like a plus. And the derivative inverse tangent is the only one that has a plus sign in it. T looks like a plus. Inverse tangent goes with the one with plus. And then both sine and secant start with an s, and so does subtraction. And they both have subtraction to them. I know these are kind of lame, but they work, right? It's worked for me for years. It will probably work for you. The other nice thing is that if you know these 3, you know the other 3 as well. So the derivative inverse sine is that. The derivative of inverse cosine is negative 1 over the square root of 1 minus x squared. The derivative of inverse cotangent is negative 1 over 1 plus x squared. And it is true that the derivative of inverse cosecant is negative 1 over x times the square root of x squared minus 1. Or if there's an absolute value, there's also an absolute value. Something worth recognizing is just like with the regular trig functions, the derivative of a co-function is always negative. So the derivative of cosine is negative sine of x, the derivative of cotangent of x is negative cosecant squared of x, and the derivative of cosecant of x is negative cosecant of x times cotangent of x. And for the inverse functions, the derivative inverse cosine has a negative. The derivative inverse cotangent has a negative. The derivative inverse cosecant has a negative. All right, here's the last thing I want you to know. Well, maybe not the last thing, but like the last thing. So an association you can make with this identity here, or with this trig derivative, inverse trig derivative, voice mix. The identity you should keep in mind here is that, let me write this right down here. 1 minus sine squared theta equals cosine squared theta. What I really want you to think about for this is if you plugged in sine for x, you would get a trig identity. It doesn't work over here. 1 plus sine squared, not a trig identity that we want. Sine squared, or not really a trig identity. Sine squared minus 1, it would be negative cosine squared, but the square root of negative cosine squared is a problem, right? Because it's the square root of a negative thing, which is not good. The same thing is true for these. If you plug in the trig function you're looking at for x, it is totally true that 1 plus tangent squared of theta is equal to secant squared of theta. It's another trig identity. Literally the identity we used to get there in the first place, right? 1 over secant squared is the derivative that we had, and then we fixed it to make it in terms of x. And the same thing is true here. If you replace x with secant, you get secant squared theta minus 1, and that is equal to tangent squared theta. So I really, really, really want you to see that when you take the derivative of inverse trig function, the thing that has, like, you're going to get something x squared plus or minus 1. You're either going to get 1 minus x squared, or x squared minus 1, or 1 plus x squared. And the correct one to get is the one where if you plugged in your trig function for x, it would turn into an identity. And the reason I'm making a big deal about this is because later on, when you take 21B, you're going to be trying to integrate something like the square root of 1 minus x squared, which I know we haven't talked about, right? This is not where we're at yet. But I just want to find out, you're gonna be like, okay, well, which of the three trig functions makes the most sense to pick for x? And it's going to be x equal to sine, because that gives you a trig. But the association, I'd be like, oh, well, I know a square root of 1 minus x squared shows up when I take the derivative of inverse sine. So sine is the choice I should be making. That's how I want you to think about this. Versus if you were trying to take, say, like the integral of 1 over the square root of 1 plus x squared, well, then I'd be like, oh, well, I know a 1 plus x squared shows up when I take the derivative of inverse tangent. So I'm going to choose x equal to tangent of theta. Again, I know this is like beyond where we're at, and you might be like, what are you talking about? Just try to remember that these relationships don't go away. They're important, they stick with us, and they're going to show back up in 20 minutes. So yeah, inverse trig derivatives, they're kind of funky. It is weird, right? So the other thing to remember is that when you take the derivative of a trig function, you get a trig function, right? Derivative of sine of theta is cosine theta. Derivative of tangent theta is secant squared theta. When you take the derivative of an inverse trig function, you get something that doesn't have any trigonometry in it at all, right? You just get this expression in x with a square root or not, right? Some kind of rational-esque thing, but not really, except for this one. So just be aware, right? The derivatives of inverse trig functions are not inverse trig functions or trig functions. They're just things that have x's in them. Okay. All right. So then, of course, now that we know how, so really, I should say, we've kind of, okay, there's like one other little thing we might talk about. But pretty much, at this point, we know how to differentiate every function that there is. There's not like anything else with maybe one minus, no, even that we know how to differentiate. You know how to differentiate everything you're ever going to need to differentiate, really. So here's our list of things we can differentiate. We can differentiate all the following things. X to a power, e to the x, natural log of x, and then inverse trig function of x. I don't want to write all of them out because I just wrote all of them out. Oh, I forgot the trig functions, right? Sorry, I should have written that one first. And I think that's kind of the whole list, right? Am I forgetting anything? Is there anything we've done that I haven't got? I mean, I know I didn't write all of that, right? So these are kind of all the functions. And then everything else we do is just some sort of combination of those things. Maybe using the product rule or the quotient rule or the chain rule, but everything else is just literally that combination of the functions we know and the rules we know kind of all scrambled together. I should also point out, right, we know how to find the derivative of stuff to a power, right? In each of these, you can rewrite it as a chain rule version and say, or, right, f of x equals some stuff to the power, or f of x equals e to the stuff, or f of x equals, I know what I left off. I mean, it's not really a leave off, but I will point it out. Inverse trig function of stuff, which we haven't dealt with yet. That's what we're going to practice right now. Although you already know how to do it. Right? If you know the derivative inverse sine of x is 1 over the square root of 1 minus x squared, you know the derivative inverse sine of some stuff is 1 over the square root of 1 minus the stuff squared times the derivative of the stuff. It's the same pattern every single time for the chain rule. Yeah, we'll definitely get to the stuff in just 1 second. I just want to finish writing this up. There were two things I didn't forget. I just don't really think of them as being different. For e to the x, you could also have, I kind of lump these together, or a to the x. And similarly, for natural log of x, you also have log base a of x. And the only difference between e to the x and a to the x is that when you differentiate a to the x, you have to multiply with a natural log of a at the end. And when you differentiate log base a of x, you have to divide by the natural log of a at the end. So let me remind you, just so you think that's worth seeing. Here are two examples, maybe 3 or 4 examples. The derivative of e to the x cubed plus 1 is e to the x cubed plus 1 times 3x squared. Versus the derivative of 2 to the x cubed plus 1 is 2 to the x cubed plus 1 times 3x squared times the natural log of 2. That's the difference. Is that when your base isn't e, you end up multiplying by the natural log of that base. Or for logarithms, the derivative of the natural log of some stuff, let's make it x to the 5th plus e to the x. The derivative of the natural log of some stuff is going to be 1 over the stuff times the derivative of the stuff, which is 5x to the 4th plus e to the x, versus the derivative of log base 3 of x to the 5th plus e to the x is going to be 1 over x to the 5th plus e to the x, 1 over the stuff, times the derivative of the stuff. And then we also have to divide by the natural log of the base. And you could definitely make it, right? I always write this out super long, which is kind of dumb. You could totally write this as like one fraction. So it's probably worth rewriting, right? This you could rewrite as 5x to the 4th plus e to the x all over x to the 5th plus e to the x. And this one you could, I don't have the space to write this here, but you could totally write this as 5x to the 4th plus e to the x over x to the 5th plus e to the x in parentheses times natural log of 3. The reason I like to write it out this way is because it kind of really emphasizes the steps, right? Here, the derivative of the natural log of some stuff is 1 over the stuff times the stuff. Here, the derivative of log base 3 of some stuff is 1 over the stuff times the derivative of the stuff times 1 over natural log of 3, or divided by natural log of 3. Questions, comments, observations? That's terrible, but I love doing it. All right, so let's do some more examples of some stuff, specifically with inverse trig functions. So what if I want to find, say, the derivative of the inverse tangent of e to the 2x? So then I have to remember so this is why you need to memorize the derivative of the inverse trig functions, because we're going to use them for chain rule. So I know the derivative of the inverse tangent of x is 1 over 1 plus x squared. So I know the derivative inverse tangent e to the stuff, sorry, not e to the stuff, but the stuff is 1 over 1 plus my stuff squared times the derivative of the stuff, which I should write on top, right? It seems silly not to write it on top. So I'm going to write this as, what's the derivative of e to the 2x? Right, or e to the 2x times the derivative of the 2x, which is 2e to the 2x. And then on the bottom, I could simplify that as 1 plus e to the 2x squared is just e to the 4x. Either way, totally fine. Or we could ask for f of x equal to the inverse cosine of the natural log of x. What's the derivative? Okay, well, I know the derivative of inverse cosine of x is negative 1 over the square root of 1 minus x squared. So the derivative inverse cosine of some stuff is negative 1 over the square root of 1 minus, instead of x squared, it's stuff squared times the derivative of the stuff. And the derivative of the natural log of x is 1 over x. And there probably isn't really anything more I can do with this. You could write it as one fraction if you wanted, or you can write it as negative 1 over x times the square root of 1 minus natural log of x squared. But that's kind of all you could do. It's really, I didn't really do anything. I just rewrote it. Let's do a couple more. Do the derivative of the arc secant of x to the 5th. Okay, So the derivative arcsecant or inverse secant is 1 over x times the square root of x squared minus 1. So here it's going to be 1 over, so instead of x times the square root of x squared minus 1, it's going to be the stuff times the square root of the stuff squared minus 1. Then times the derivative of the stuff. So it's going to be 1 over x to the 5th times the square root of x to the 5th squared minus 1 times the derivative of x to the 5th, which is 5x to the 4th. And if you are lucky and get to use the version without the absolute value, you can do some simplifying, right? 5x to the 4th over x to the 5th, I can cancel out an x to the 4th and rewrite this as 5 over x times the square root of x to the 10th minus 1. And you could probably even manage to do that if you had an absolute value, so be a little bit careful. Does anyone know if which version of these derivatives they are using? It's okay if you don't, but like if you do know, I can certainly tailor it to do it the other way if you wanted. Right? I suppose our answer could be or 5x to the 4th over the absolute value of x to the 5th times the square root of x to the 10th minus 1.
Of course, he doesn't do absolute value.
Okay, good to know. And I would mention here that you totally could simplify this. I'm just going to point out, again, this isn't super important. You could totally break this apart like this. So the nice thing about absolute values is the absolute value of a product is the product of the absolute values. If you multiply two things together and then take the absolute value, it's the same as if you take the absolute values first and then multiply them together. Either way you do it, the end result is going to be the same positive number. So I can totally break this up like this, but then I should just point out that the absolute value of x to the 4th is just x to the 4th. Because if you're being raised to an even power, you're always going to end up being positive. So I can totally be like, oh, well, that's really just actually normal x to the 4th. And I totally could cancel this with that. So if you wanted to simplify this, you could write it as 5 over the absolute value of x. I'm just going to x to the 10th minus 1. So yeah, if you have an absolute value, though, it is kind of a pain in the butt. Let's look at one more, maybe one more example. Let's do f of x equal to the inverse cotangent of the square root of x, which I would encourage, no, let's write it this way. So the derivative is going to be, let's see, it's 1 over 1 plus, oh, I forgot something. That's all right. My stuff squared times the derivative of my stuff. And what did I forget? Let me remind you, it's the derivative inverse cotangent. Negative. When you hear a co, you should think negative derivative. Okay, there is one exception to that. If you guys talk about the hyperbolic trig functions, that doesn't hold true. But not everyone covers hyperbolic trig functions, so let me know if you see them in class. Has anyone seen hyperbolic trig functions in class? Okay. They might not have just said they're hyperbolic trig functions. So if you've seen something like e to the x plus e to the negative x over 2, you have seen a hyperbolic trig function. They just didn't call it that, which is okay. You don't have to know the names of it to still deal with it. If you haven't seen this, don't worry about it. But if you have seen it, we will definitely talk about it. We'll probably talk about it anyway, but like we don't need to talk about it right now. I would simplify this a little bit. So this is going to be negative 1 over 1 plus x. And the derivative of the square root of x, I do think it's really worth memorizing. I know you could totally write it out as x to the 1/2. And then the derivative of that is going to be 1/2 x to the minus 1/2, which you could then rewrite as 1 over 2 root x. The derivative of the square root of x comes up often enough that I think it is worth memorizing and just knowing that, oh, the derivative of the square root of x is 1 over 2 root x. And then I guess you could throw it all together. I don't really want to, though. I would probably write my final answer as 1 plus x parentheses times 2 root x. I probably would have put the root x in front, but I ran out of space, so I can use that. Oh, yeah. What time is it? 11:34. All right. So let me ask you all. What else are you guys doing right now? And for you on Zoom as well. Like, I know people are all over the place. So I know Velocity is like way all over the place. For people, even if you're in Velocity class, are people talking about related rates yet? Blank faces. Anyone talking about related rates in the Zooms? You did in Jacob's class, okay. And then what other topic was I kind of looking ahead towards? Oh, where'd you go? There was something else. Oh yeah. And then so the things I'm kind of eyeing coming up are related rates, linearizations. It's okay if you haven't heard it, it's okay. I'm just looking ahead. So linearization is a fancy word for finding the equation of the tangent line. They make it sound very complicated. Linearization is like super straightforward in the beginning. You're just like, oh, I'm going to find the equation of the tangent line at a point. And then you're going to use that tangent line to estimate the value of the function. Because it's way easier to plug something into a line than just like a square root function. That's coming up as well. I guess, are there things that you guys have seen that I haven't covered? Like, I'm trying to think back to anything you might have missed. No one's doing graphing yet, right? Like talking about maxes and mins and stuff like that. Okay. Oh, that's right. The mean value theorem is definitely something that people have. I've seen people have seen. It's always hard because at this point people kind of go in a lot of different directions. I mean, they kind of just. It's not that they go in different directions. They kind of like, I'm going to do this first and then this and then this, and kind of scoot back to the same place. So, let's see. Totally, yes. You guys are always welcome to ask questions. It's okay to ask questions from the homework. I don't mind. Or not from the homework, other places too.
Remember an x approaching 0 of the quantity of e to the x minus 1 over x.
And let me ask you, what tools do you have available to you? Are you allowed to use L'Hopital's rule? Okay, that's what I thought. Good. I mean, not good, but perfectly fine. So here's what I imagine they want you to do. Here's the limit definition of the derivative. And you can also, so that's the derivative at any value x. But you can also write it as at a point A, the derivative is the limit as h goes to 0 of f of a plus h minus f of a all over h. Or using x instead of h's to make it more similar to this, you could say that f prime of a is equal to the limit as x goes to 0 of f of a plus x minus f of a all over x. Does anyone have issues with what I've done so far? Other than why would I use x instead of h? Because they're using x instead of h there. Okay. I'll ask this right away. I'm interested in finding the derivative of a function at 0. That's going to be the limit as x goes to 0 of f of 0 plus x minus f of 0 all over x. Or if you prefer, a limit as x goes to 0 of f of x minus f of 0 all over x. So let me ask you all, what function does f need to be so that that limit is the limit I want it to be. What's that? Go ahead. Yeah, I want this to be e to the x and this to be 1, which is e to the 0. That works out. So what I have here is that the right-hand side is the limit as x goes to 0 of e to the x minus 1 over x. And that's for my function e to the x. Okay, so let me ask you, what's the derivative of e to the x? E to the x. So this left-hand side is literally the derivative evaluated at x equal to 0, which is just e to the x evaluated at x equal to 0. Which is just 1. So the idea behind this question, I believe, is that they want you to see that it is really the limit definition of the derivative of a function evaluated somewhere. That's the whole point of this question. Let me show you another example that's similar. Let's say I want to find, let me think for a second here, make sure I don't make it stupid. I want to find, sorry, my brain has to like work out a problem real quick here. Yeah, we can do that. Okay, let's find the limit. I don't want to do that. People do it this way, fine. No, that's dumb. I don't want that. Sorry. That's too. So the problem with this question here is you could totally just do this by factoring and canceling. It's not like super easy, but it is doable. Yeah, that's not what I really wanted. I think I want something more like this. The limit as x approaches 0 of x plus 2 to the 5th minus 2 to the 5th over x. Yeah, that's more terrible, but also easier. So you could totally multiply this out. X plus 2 to the 5th is within the realm of reason. It's a little bit unreasonable, but it's not totally impossible. You can use Pascal's triangle. But again, that's not the point. The point here is to recognize that this is the limit definition of the derivative of something. So my function is something like x to the 5th. Is it x to the 5th? I don't actually know. It might be x to the 5th. Yeah, I think it is. And I'm going to be, so how do I'm like trying to think about, the problem is I know and this is what they do, they use x here instead of h. Right? H would be a lot nicer because it makes more sense to me. So that's actually what I'm going to do. I'm going to re-express this in a way that makes more sense to me. I would say, well, this is the same as if I just use h. Right? Those are the same. I can replace every x with an h, and it should be the same thing. So this is the derivative of something evaluated somewhere. I know that f prime of x is the limit as h goes to 0 of f of x plus h minus f of x all over h. But I don't have x plus h and x. What do I have instead in this expression? Instead of x plus h, I have, right, or 2 plus h. Instead of x, I have 2. So what I'm really thinking here is, oh, well, if f prime of x is this, f prime of 2 is the limit as h goes to 0 of f of 2 plus h minus f of 2 all over h. That's the idea here, is that we want to see that this is really the derivative of a function evaluated at a particular point. So you can say, okay, well, this equals f prime of 2 for what function? Right? Like I said, it's the derivative of a function too. What is actually the function? What is the function? Well, if I'm plugging in 2 plus h or h plus 2, and then what am I doing to it? I'm raising it to the 5th power. So it looks like my function is x to the 5th. Let me let that sink in for a second. Is this really the derivative of x to the 5th evaluated at 2? I think it is, right? If I want to, let's actually write that this way. If I want to find the derivative of x using this function, it's the limit as h goes to 0 of x plus h to the 5th minus x to the 5th all over h. Oh yeah, and if I plug in 2, it's for sure true. And that's going to be the limit as h goes to 0 of of 2 plus h to the 5th minus 2 to the 5th all over h. So these problems, if they're just like on web work problems, they're meant to be short. Yeah, they require a bit of thought, but in the end, the expectation is kind of like, oh, the student should be able to see it's a derivative of a function and then just take the derivative and plug in the value. So we're like, okay, the function is x to the 5th. The derivative is 5x to the 4th. And the derivative evaluated at 2 is 5 times 2 to the 4th, which is 80. That's it. It's a process, but the calculation part is not too terrible. Yeah, it's a good question. But definitely, when you see a limit like this, and it looks like, especially, it looks like it might be like the quotient kind of the difference quotient kind of limit, where it's like the limit definition of a derivative. You should be thinking, I might just be wanting to think of this as a derivative of something else. That's often what they're going for at this stage of the game. Certainly, and especially for things like, so just to back it up a little bit, like if I gave you this example or even this example, it totally is something you can multiply out and cancel stuff and actually just do the limit. Or you can totally multiply this out and get, x to the 5th plus 5 times x to the 4th times 2 plus a bunch of other things, and stuff cancels. The limit works out to be 5 times 2 to the 4th once you cancel this stuff. But there was a point that I was getting to. The point is that for the one that they gave you, which was e to the x minus 1 over x, there isn't really a way of simplifying that, but you're stuck with it, right? You can't like rewrite e to the x as something else. So you have to kind of start thinking of other ways to attack this, which is using the limit definition of the derivative. I mean, that's not entirely true. There is kind of a hand wavy thing you can do with e to the x to make the limit work, but I really don't think that's what they meant for you to do. So, yeah. Other questions?